Okay, everybody. So this video, we're going to do a short overview of the design project that was assigned on Tuesday and is due a week from this Tuesday. I'll point out here that you'll submit with this a final report. You can also submit your code or spreadsheets or whatever you use to do the calculations as appendices, but all those need to go into Teams. And then I will ask that those submissions be no zip files at all. Okay, individual files only. Zip files are very hard to handle for the TAs, so please do not upload those and upload them individually or combine your PDFs. And no late work will be accepted. Okay, so an overview of this project. Basically what you're doing is I'm asking you to do a redesign of an organic Rankine cycle system that was designed and constructed for this class. Here's a schematic of a device that under normal circumstances we would actually be able to go over and touch and operate, but with COVID we're unable to do that. Here's some of the components, the major components, including the expander, right? You have the boiler. This system actually has two different styles of boilers. We're just going to account for one. It has a pump, positive displacement pump here, and then it has condensers. It has a couple different kinds of condensers. One of which is actually a refrigerant to air condenser, but that condenser is too small. So your task is to redesign this loop to make an air-cooled system that can run in its entirety with an air-cooled condenser, and it will need to generate at least 400 watts of net power. And you'll see that the overarching goal is to actually come up with that heat exchanger design using the rest of the existing equipment here. What you'll deliver with the project is a complete final design along with the evidence that that condenser satisfies those design, including some metrics like the complete cycle power generation, so the power generation in kilowatts, the thermal efficiency of the cycle, that's really just for reference, and those are at a given environmental conditions that are at the bottom of the document. And then a list of the final design metrics, specifically the condenser, which I'll enumerate down below, and a short report summarizing this. And for the report, I'll point out, use the template. It has tables pre-populated for you. It has formatting with sections put together for you. You need to use it. Okay, and then you can supplement that report, as I mentioned, with any code or analysis to generate those outcomes. Okay, so that's overarching, and now I'm going to go through the individual sections which talk about how to handle each component in the ORC. The expander, we're assuming we're going to use the existing expander. And we have some information on how well that expander works. We know that it rotates at a certain rotational speed, 3,600 RPM, and it has a certain displaced volume. And you also have some steady state test data, and we're assuming that you've taken that and you've converted that into an average efficiency and measured that it has an isentropic efficiency that is 70%. Then you're given some assumptions about the expander, that it's adiabatic and that its irreversibilities are identical at all environmental conditions. And you're asked to use that information to develop a model for the expander for use in the design activity. Okay. Then the final report should include two things. First is the fill factor, which we discuss in the expander analysis portion of our ORC discussions, and the net power and the power generation by the expander itself. So note that's not the net, that's just power generated by the expander. And then here below is where I define the fill factor, which we also go over in lecture. The pump is a diaphragm pump. It's positive displacement. It's assumed to also have a fixed isentropic efficiency and is adiabatic. And in the final report, I want you to give the pump power at the given conditions. So pretty straightforward. The boiler, the existing boilers in there, there's actually two. There's a brazed plate and a concentric coil, but they're both refrigerant to water heat exchanger. We're assuming we're going to use the brazed plate, and we're told to assume that the exit temperature of the boiler will approach 10 degrees F as a given source temperature. So that means that the refrigerant temperature will end up being within 10 degrees of the source temperature. It means refrigerant gets to within 10F of source temp. Okay, and that should be all you need to actually generate a model for the boiler. And then using that information, I want you to report in the final report the total heat input to the boiler. So those three components will need to be coupled together in a cycle analysis and combined with a more elaborate model for the condenser. So the condenser, I'm giving you lots of geometric information. The first of which is a total space to constrain the design. I'm telling you have this big a box to fit your heat exchanger into. And you're told that the maximum length is 19 inches with a height of 16 inches. That's the maximum tube length, and I'll define those visually here in a second. And then you're to assume that you're ending up with a 10F subcooling out of your design, and that you have basically ultimate flexibility with the number of tubes that can exist within this package window. The things you can vary are the tube diameter, which you can vary between these two quantities. You're told you can ignore the thickness of the tube itself because we're ignoring conduction like we did in the condenser analysis. And that we're limiting the number of rows, which I'll define, to 5 rows deep. Okay. And then the length of each tube can be up to the envelope described, right? Meaning it's a maximum of 19 inches long. The tubes are then spaced 1 inch vertically and horizontally, where the horizontal rows are offset by ½ an inch. So what does that mean? That basically means if here's your cross section of the fin tube heat exchanger, right? The length of the tube is in and out of the page here, but then you have a number of rows where every inch there is a tube. So if you have an upper limit of, say, 16, so this is the height. Oops, pardon me. So this is your height. All right, if that's your height and you're limited to 16 inches, you can have 16 tubes in that first row. The number of rows deep is shown with 3 in the figure. You can have up to 5. You're also given some information about the coils itself, because we're assuming we're not actually making the coils, we're buying the coils. We're buying them from this company, this AB Coil Company. And the company's telling you that, okay, for the particular type of fins you're selecting, you're actually going to end up with a ratio of area of 21, where the air side surface area is equal to 21 times the refrigerant side surface area. And you're also told that for these fins, the overall efficiency is 0.85. They've also done some experiments internally in the company, and they've given you some heat transfer coefficients. They have given you directly the air side heat transfer coefficient, and then told you that the refrigerant side is again a ratio of that. It's 41 times larger. You also need a thing to move air over these devices, and you have 3 options you can select from with different blower fans. Each design gives you a different CFM. They're sort of different size wheels, and you can select from either 1,000, 1,200, or 1,500 feet cubed per minute of airflow. And then you're also told that you can ignore the electrical power associated with the fans. Okay, so you can, or then you're asked to report a bunch of things about the geometry, including the tube size you select, the number of rows that you select, the total number of tubes that equates to in the heat exchanger, the final air side surface area, the selector blower fan rate in CFM, and then the calculated final package size in length, width, height, and then the net heat rejection from the condenser. Right, that's your Q dot condenser. So you want to model all that with one given set of environmental conditions, where the source temperature, that's the water side temperature going into the ORC, is 170 Fahrenheit, and that the condenser air inlet is 60. And then finally, you need to put in a final report. These are just some notes here. Again, use the template that I've given you on Teams. It must be based on the template, right? And I do encourage you to put some thought into the words you put into the report. You want to make sure that somebody could follow along with this and replicate it should they take this class again. Okay. And finally, use appendices after the reference section. So some broad advice is to start with a simple system model. Start with a Rankine cycle system model like we went over in class. Then realize that you may need to add some more complexity to these models. Specifically, you're going to have to add a more complex condenser model. So then think about, how am I going to replace the condenser model in my existing simple thermodynamic analysis with a more complicated one? And I'd go back and refer to the lectures on system analysis, where we did some E's, where we integrated condenser and compressor models. Okay, so that's one bit of advice. The other is related to the heat exchanger geometry. And I wanted to spend a little bit of time telling you about the heat exchanger geometry. Here's a rough picture of what a fin tube heat exchanger sort of unit cell might look like in this design, where you have a bunch of tubes. This is a tube. The yellow bit's a tube. And it has fins, right? And your air's blowing across it right here. Okay, and if I were to take a single tube out of that and look at its cross section, it's going to have some diameter, D, and some length, L. And if I wanted to calculate the area on the refrigerant side of that tube, how would I do that? right? I would just take the circumference of that diameter, which if we're ignoring the thickness, we're just assuming the thickness is 0 effectively. You take the circumference, pi d, right, times the length of the tube, times the length, and then multiply that by however many tubes you have in tubes, and that's going to give you the total refrigerant side surface area, right? And then realizing that each one of these components, right, is a variable, meaning you can change this parameter. You have control over the diameter. You have control over the number of tubes. And so what you need to determine is essentially what do these parameters need to be to achieve your goal of 400 watts. That's your overarching objective. Okay, I hope this added a bit more clarity. If it does not, certainly reach out to myself, the TAs, Professor Southard, or post something in the Q&A channel for us to address. And then finally, get started immediately. If nothing else, put your simple cycle model together and start working on it and see how far you can go.